So just remember, this is our material I've taken, not my material. It's from the Royal Statistical Society website, last the continuation of last time's talk. So these materials are copyright, not copyright, you can use them because I'm just using for teaching from the Royal Statistical Society. So last time I just told you why we do data visualization, and I hope you just got an idea that why we should do it. Today I'm going to take some principles of it, right? So that's just some principles. So there are, when you show a picture, there are 4 or 5 things a picture should do. The first thing is there must be some sort of story you're trying to tell. A picture conveys 1,000 words. So the picture must tell, every picture must tell some story. So you must have, as a statistician, biostatistician, doctor, you must have some story in your mind you want to tell. That's the first thing. Then what's the goal? I have a story, but I want this picture must convey one message to the audience. Third, I must look at the data. Okay, and I have so much data. What is the best way or simplest way to present the data? Some people make complex graphs so that people, oh, this guy knows how to make a complex graph, but nobody can understand the data because it's very complex. Make it simple so people can understand. Lastly is visual form. Okay, I can make Venn diagram, bar diagram, split diagram, this diagram, that diagram. Which form am I going to choose? So these are the 4 components of making data visualization. So what are they? First, you must have some data to present. Then a story. What is the story I want to tell? The third one is what is the goal? What is that main message of this slide? Last one is which visual form I'm going to use. So this comes from this information is beautiful.net picture. And all the marriage of all these together is successful data visualization. So you must understand what is the purpose behind the graph your picture trying to make, and assess whether sometimes you make a graph. This is your own colleagues. Hey, I made a graph to show this picture. Do you think it really demonstrates nicely or not? So that's an important thing to do. The most common purpose of data when we bring graph or table is when we compare 2 groups of people. That's where a graph or table is useful. Making comparisons, graphs are useful. So a good choice of x-axis, y-axis, data points helps identify patterns, even symbols. If you don't make good choice of x-axis and y-axis, it will hamper your data or the story you're trying to tell. So let's have a look at this picture. This is from the BMJ. I told you now, abstract data, visual abstract has become a big science now. Once we try to think, Mercy did a critical appraisal of visual abstracts. So you can say this is when statisticians have data, they also have something called code. That means the mean and median or the height and weight I converted to BMI by writing a statistical command. That command is also called the code. So often when you share your data with other people, you're also supposed to share your code. You have the raw data. How did it get converted into height and weight become BMI? Or how did you calculate survival analysis? What statistical functions you use? So data and code. So the question here was how many people actually share the code when they do in the journal article, they say we will share our data and code. That is a question. That's a question. Now, sometimes when we do the research, the final answer will be like Sherlock Holmes. The last paragraph will be the answer to the question. But nowadays, data visualization, you must tell the answer straight away. What's the answer? Medical researchers do not share the data or code easily. Oh, that's the answer to my question. If that's all I want to see from the picture, my picture is over. What is the study design? Systematic review. Oh, I collected from 2 million publications, of which 105 were already meta research. What is the quality of the data? We know that red generally means danger. 87% were high risk of bias. Even if somebody doesn't understand risk, red, oh, okay, it's not a very good thing. Then, this is the graph, okay? And you can see that there's one graph here, 2012 to 2020, another one, 2012 to 2020. The one in green is declared prevalence. That means I am going to share my data. Actual prevalence is when people contact the people and say, Thambu, can you share the data? Like, oh, I don't want to share the data with you. So what I proclaim to do and what I actually do, these are the two graphs. And you can see that the proportion available is only between 2012, it was nearly about 3 to 4%. And by 2020, it's only gone up to about 10% of people are actually sharing data and code. But if you look at the actual, this is what they claim to do. This is what, if you write to them, this is what will actually happen. What about these circles? This is the size of the circle is proportional to the log of the sample size. So the picture gives so much information. You can convey all in just a single picture. So that's why I'm trying to say that increasingly you have to start thinking about all these things, not to make one graph and submit it. And this is often the only thing people will look at. They won't read your whole article, but everything in the whole article is given in one single picture. So let's go one by one. What are the various elements of a chart? So, and then what are the software which people use? Very often people are stuck with software. Oh, I want this software, I want that software. It's not really the software, it's what's in your mind. What are the data I want to tell? What's the story I want to tell? What's the main message? And what kind of picture I want to use? So don't get stuck and say, I don't have this software or that software. So let's look at this. This is called a layout. These are called panels and facets of data. So you can see here that this is on the x-axis, the displacement of the engines, and this is the mileage in the city. And these are four different types of engines, and the displacement could be 2 liters to 7-liter engines, right? So when the data are on the y-axis are to be combined, if you want to compare data on the y-axis, then this kind of data helps. You can compare how many had 15, 20, 25, 30 of the mileage across different displacements of engine. If you want to compare data on the x-axis, then the data panel should be stacked vertically. On the other hand, if you want to show multiple data, then you have to have a different idea. Let me show you one with multiple idea. Okay, you saw this graph. What is good about this graph? The x-axis seems to be divided into many similar x-axis, but the y-axis is one. So though I have 1, 2, 3, 4 panels, I can combine all easily into one picture because I've made the y-axis common. So instead of putting 4 separate graphs, I can combine them all into one graph and show the data like this. Yeah. So this is how you must use layouts. Now sometimes you have to use more complex graphs, matrices, or layouts. Now, on this axis of this table is the name of the human being. Fred, Bill. I've taken this picture from this particular website. So these are the name of people. And they're looking at your skill in a business. What are the two skills they're looking at? Procurement, your skill in buying something or the skill in negotiating with somebody else. What do these colors mean? If you're very good in that particular skill, your blue color, you're called a guru in that skill. If you are not so good, you're called trained, a spelling mistake. And yellow color is you're familiar with that skill, and 0 is you're not very good at all. So you can see that for Fred, procurement skill is trained level, whereas Steve is for procurement skill 1, he is in guru level. So much information could be produced in one particular graph, but you have to choose carefully the axis, the layout, and the paneling to convey this information. So you have to think, this is so much information that I want to convey in one picture. This is panels and facets. Okay, on the y-axis here is time. Okay, and this is on the, on the x-axis is time, 0 to 24 hours. I'm comparing drug concentration. I give a drug, and each line represents one human being. So pharmacology studies are done like this, and it is over 24 hours. Initially, the drug concentration will be high after I give, then the drug concentration will come down. I want to look at whether low body weight, medium body weight, high body weight affects the drug concentration. So how does it affect drug concentration? Right. So let's ask somebody. Would you like, these two graphs are exactly the same. Which one you think is useful for helping you to compare? What's the difference? Yeah, somebody looking at the picture. I'm not asking you some test question.
Concentration seems to be higher and lower.
No, the difference between this graph and this graph, they're both the same data.
Yes, sir. The comparison.
Both are same number of variables. What's the difference? You see here, you can see the low, medium is kept like this. Whereas here the low, medium and high are kept like that. What is the advantage of keeping low, medium and high like this as compared to this? Yeah, you can. What happened to the y-axis here? The y-axis became common. So now all of a sudden you can compare everything across, right? So when you see on the left-hand side panel, here you can see that in people with low body weight, it seems to be high, and in medium body weight and high body weight. You can compare across body weights like this because you have stacked the panels this way, right? So the layout on the right side is often preferred when you have this way. But if you put in the software SPSS or R or ggplot or whatever, it will produce whichever way you want. It's a click of a button. What you want on x-axis, what you want on y-axis, how many panels you want. You must do both and then have a look at it a little bit and think, oh, okay, I think this one makes more sense to me. Because I'm trying to compare across the three body weights, and this one visually gives me a better image. So this is about paneling. Okay, the key thing is that the y-axis is the same for all three here. But here I can't, I've done separate. This one helps because I'm trying to compare the y-axis, right? So this is one thing about the paneling of aspect ratio. Aspect ratio is the relationship between the x-axis and the y-axis. Generally, as far as possible, all medical graphs try to keep it as a square. It avoids bias of inflating the x-axis or inflating the y-axis. So, if there's something common between the x and y-axis, always keep it as a square. What should be common after that? Before and after. X-axis is before the drug or some measurement before, y-axis is after. Or there's the same thing as kilograms or meters. As far as possible, try to keep it as same and 1:1 ratio. So it's a good default if you have, for example, let me say sensitivity and specificity. What is that graph called? Anybody? A diagnostic test, and y-axis is sensitivity, x-axis specificity, ROC curve. Always it should be a square because sensitivity from 0 to 100, specificity 0 to 100. So the graph should be square. Very often people will make one axis bigger or smaller to try to make some sort of story which they're trying to sell. So you should always be careful of that. Okay. Now, suppose I am doing a prediction model. Okay. What is going to happen to the medical students' final year marks? What are their actual marks and what I predict? Okay. What's on the x-axis? And the y-axis is? This is called calibration plot. This should also actually be only a square. Can you see that when I have a square, it looks like this? These are the actual points, okay? And this is the fitted line. A diagonal line means perfect. So in this plot, I can show that. And this red line is actually supposed to be a fitted line to all these curves. You can see that what has happened here? Middle panel. I stretch the y-axis. What happened here? X-axis. So I can change the story. The picture may change your interpretation. This is the correct interpretation. But if I make it look like this, you may think, oh, there's a sudden change in there's a big, huge change in the observed compared to the predicted. You may say, no, the predicted seems to be going quite different from this. It's just a visual trick. So never fall for the trick. You should not, when some journal produces a graph like this, you should say, hello, what is that? It should be 0 to 100. Here you put 50 to 90. So you can change the number of plots. Everything should start at 0 and end at 1. So you should be very careful when you do these kind of tricks. Always stay, if you're not sure, 1:1 ratio is the correct default option. Okay. Okay, next we're coming to lines. Okay, this is an article published in the British Medical Journal. On the x-axis is the year 2011 up to 2015-16. Each point, and this is the average score out of 10. Okay, they're instead of putting 0 to 10, they only showed 7.2, 7 to 8. Okay, because they want to actually, if you had put 0 to 10, probably all the lines would have been together. They have stressed the line. So that's the first thing to realize. Oh, when you look at the x and y axis, if the score is 0 to 10, then where is the 0 and where is the 10? This is done to inflate to show the difference. The second point you must understand is that there's an order to this. There's a point here, and there's a point here, and there's a point here. Should we connect the lines or should we not connect the lines? What do you think? We're trying to show a trend between, is there an increasing trend or a decreasing trend? So then you can connect the lines. There's a reason to connect the dots, otherwise don't connect the dots. You connect the dots when you're trying to show an order or a sequence. Okay? Otherwise, the data should not be connected by lines. When you connect the lines, there is something to connect them. What is this? Over time, how does something change? Different line types indicate different groups. What are these colors? So this is looking at your happiness. The light blue is life satisfaction. Green is happiness. Red is worthwhile or not. You feel worthwhile or not. And your self-assessed health is very good or not. So the colors help you to differentiate. Although don't simply put colors because it's nice to put colors in lines. Okay? And there's an inherent order. So you can say that this is one, this is one, this is one, this is one. There are 4 different types of subgroups of health. They have split it up. So the order is put in different colors. Okay. Sometimes we can do things like the line thickness. The thicker the line generally means more data. But dash density means that maybe it is not actual data, but predicted data or model data. It may be. And the darkness of the line may indicate higher quality, lower quality, more data, less data. So we must be very careful how lines are done. So I'm going to show you one example. Okay, now let's look at this one first. We're trying to compare for people with less bone density. As you grow older, you get osteoporosis, right? So then what are the good drugs for osteoporosis? So you want to increase the bone density. So this is called a network meta-analysis. So which is the biggest circle here? That means maximum number of studies have been done with vitamin D compared with placebo. You can see the thickness of this line. That means most of the studies are comparing vitamin D with placebo. What do you think the red line means? There's some red color lines. Yeah? Nice. High risk of bias. So those studies generally seem to have, there are some studies there with high risk of bias, means they're not done very well. Green generally means low risk of bias. What does the dotted lines mean? Who likes maths? You like maths? Yes. So can I compare with this? Why is there no line between ipandronate and zoledronate? Sometimes we give ipandronate once a month. Sometimes we give yearly zoledronate. There's no line. What does it mean? There was no randomized control study comparing ipandronate with zoledronate. You like maths, no? Can I make a triangle out of this? If I know 2 arms of triangle, can I make out the third arm? You said you like maths and trigonometry. If I have 2 arms of a triangle, can I make the third arm? Make up your mind, like you're not saying. Yeah, you can. So that's called, this is a direct effect. Direct comparison of zoledronate with vitamin D. This is a direct comparison. I can put a dotted line here, and that will be the indirect effect. So usually dotted lines are shown for indirect. So mathematically calculated. But you must give a legend in the bottom to say what did you mean by it. I may mean something else by dotted line. You may mean something else by dotted line. So the lines are very important, right? So this is the interpretation of lines, circles in network meta-analysis. Points. Points and symbols should be chosen that it's a meaningful way. Should I put a dark dot? Some people like to put a big white dot. Some people put a small white dot. Some people put X marks in the graph. How should we put the points in a graph, right? So generally the useful way is if you have lot of data to be shown, right? Small open circles are generally preferred, right? Then if you put dots with, if against every dot, if you put the value, the graph will look very untidy. So small open circles are generally better. So I'm going to teach another thing called jittering. Has anybody heard the word jittering? Jitter. Jitter means like, okay, so jittering. So this is a comparison of petal length with petal width of stars. And it is taken from this particular blog on how to make pictures. There were 50 comparisons between petal length and petal width. But this picture shows only 22 points. This is the fitted line between these two. Does the line look correct to you? That's the ideal line. There are many points above this. This line seems to be slightly below. Maybe they could have pushed the line up slightly. So when you see the scatter plot, you must always ask, how did this fitted line come like this? Now the thing is, there are only, of these 50 points, which they showed only 22, about 28 points were repeat observations, meaning the same petal was length and height was checked 2 times. So they decided not to show the repeat observations, only showing the single observation. So that's why there are only 22 points. But still people will think that there are, this line is slightly lower than it should have been. I think it could have been slightly high. So now let us look at the next one. This is exactly the same graph as the one on the left, the one on the right. What do you notice about the number of points? Same number of points or more number of points? More number of points. Remember, I told you the small circles, small empty circles are beautiful ways. What they've done is something called jittering. For every point, you can add an extra point, which is 0.5 more, and another point, which is 0.5 less. Will the average change then? Average won't change because for every point I've added 2 extra points, one more and one slightly less. That is called jittering. The effect of jittering, what has happened? Now when I do jittering, let's look at these 3 graphs. This was the original graph with 22 points. This is the jittered graph. I've added just 0.5 more and 0.5 less. And now when I draw this picture, you can see this is the jittered graph, but this is the same axis as the original graph. I have not changed the original graph. But now suddenly, because I add the jittering effect, the number of dots below and above the line appear to be same. So now I feel like a little bit more comfortable in producing this graph. Actually, this is the original data. But people are saying, hey, these points now are not reflected in this line. I simply added something called jittering effect, which didn't change the overall average. But these are not original points. So when people put jitter, the reader must understand this is a jittered curve, a jittered graph, to make the picture look more visually appealing. But this line is not the line of the jittered curve, but the line of the original data. So this is called jittering in scatter plot, right? Okay. What about colors? As you can see from my presentations, I like colors, but generally colors are to be avoided in graphs. So you can see here, this is the location from Africa, Tanzania, Kenya, all the way to Senegal. And this is a number of articles on some particular topic. The colors are coded on whether they had less than 1,000 lines in that country, more than 1,000 lines, and red means possibly the lines have become extinct in that. So what is it? Dark color means more. Gray color means gray or not grayer. Gray color means less. Red is extinct. So we just or just put black or gray scale. If you choose gray scale option in graph, it is as good as doing many colors. So that's an important principle to remember. So when you're comparing different groups, using color is generally discouraged. Natural shades of gray are very easy for the human eye to look and interpret. So black means more, then slowly gray goes down. So this is an order which you must always try to do. So that's the key thing that you find even in any JM or Lancet or top journals, most graphs are just black and white with different shades of gray. Okay. Now, what about the axis? Now, this is comparing dapagliflozin versus placebo. So let's ask this, Mercy. What is the big graph? Y-axis, x-axis is months from randomization. X-axis, Y-axis, cumulative incidence of death. Which of the two graphs is correct? Or they are two different graphs? Eva, what do you think? What do you think?
Either axis. So the overall picture and this is the inversion of it.
So this is the correct picture. 0 to 32, 0 to 100. What is the difference here? 0 to 12. What am I trying to do? This small difference I'm trying to magnify. As a doctor, you must look at this graph. If you are a farmer rep trying to sell dapagliflozin, you sell this graph. So nowadays journals have put a trick. They put both so that they can't be accused of misleading anybody. Hey, if you're so smart, you look at this. I'm showing both, so you can decide what to do. So choice of axis is very important. So if you really want, I'm not saying you should not try to sell this, but put both at least so that the reader can be sure that what is the real difference between the two. Choice of axis. So the origin 0 to 32. Here 0 to only 12. And the limits are very important. Generally, make sure your axis start at 0. Avoid starting. Sometimes they put 0, then you'll find one double line here, and the next point here will be 80, and the next point here will be 100. Because to fool you that it's from 0 to 100. No, it's not. Look carefully, 0, the next point is 80. So they do all sorts of tricks to make you think that the axis is fine. So if there's no negative values, sometimes you'll find that the software will give you, -4, -8, and here it will give you minus. So you can't have a minus depth and you can't have a -0 time. So then you should make sure that the graph should be corrected for that. Some software will automatically turn out minus values. So just be careful that there's no minus value shown in the graph when there is no minus values. Okay. Now let's see what you learned. Which graph is better? Sorry. Hang on. Which graph is better? What would you do if you were a farmer rep? Yeah. Is there any difference in the two graphs? Difference in the difference between our product and competitor? Is there any actual difference? So the difference appears to be 220 to 210, maybe 10. What is the difference here? 220 to 210, maybe only 10. But this suddenly appears to look great. What's the correct way? This one. What's the wrong way? Right. Okay. So deliberate choice of axis of y-axis limits can make a big difference to perception. Right. So, and therefore interpretation by the reader. So you must always be careful that we don't do this particular mistake. Okay. What if the x or y axis is not numbers, but relative risk or odds ratios? Let's ask the stats people. Relative risk of 4 means more or less. Your risk of death is 4 times mine. More. What is the minus equivalent of that? The protective equivalent of 4. 1/4 or 0.25. So in a graph, 4 and 0.25 or 1/4 should be the same distance from 0. So suppose I say your risk is 4 times my risk. The relative risk is 4. Suppose I compare mine with yours. So 4/1 became 4. But it just depends who chose the numerator and the denominator. If I compare the other way, 1/4 is the same as 4/1. On a graph, 1/4 should be same distance from 1 as 4/1. That's an important principle when you're doing odds ratio or relative risk in a graph, right? So the corresponding axis should be called logarithmic. It's called logarithmic scale. So today we're going to learn a little bit about logarithmic scale. So 1/4 should be the same as 4. What is the point of no difference in relative risk, Anuka? 0 or 1? Your risk and my risk are same. Suppose we divide the two risks together, 1. So there should be a line showing 1, and then one side can be 4, one can be 0.25 or 1/4. But the distance from 1 should be the same, so that the reader is not fooled by the picture. We can show other gray marks or red marks to help the person understand. Let's understand this picture. Can somebody interpret this picture? This is comparing tranexamic acid with placebo for women with bleeding, and the relative risk or risk ratio is the picture. What does the line of 1 mean? Equal. So the first study, Sentinel Health 2018, the relative risk point estimate is 0.82, which is protection. But the confidence interval is crossing 1. 0.56 meaning lot of protection. 1.21 means this side. But the picture tells more than this. That's why people like picture. What is this vertical line? Relative risk of 1. You can see relative risk of 10 is here. That is 10/1. The same as 1/10. The distance from here to here should be the same as distance from here to here. So this is a graph on logarithmic scale. Yeah. Everybody clear? This is how a graph should be done. So an example, we want to know some y variable, how it changes depending on a x variable. Okay. So does blood pressure change with treatment? As treatment changes, how does the blood pressure change? All right. Look at these. This is the x variable. This is the x variable. Focus on the top half of the graph first. This is the y variable. This is the amount of change in blood pressure, and this is the amount of change in blood pressure. What do you notice about the two graphs? Anybody? This is also one. This is also one. Which one looks more appealing? This one. What have they done? They pushed the one up a little bit so that the number of dots below and above are the same. So the data shown on average, no change compared to the baseline. Baseline, how do you know? One is put in a color. So when you have logarithmic scale, like I showed you relative risk one line, here you can show the red line. So that visually people understand data points close to the red line is no difference. Right. The only difference here is I've changed the graph so that this has equal distance before and below and after the no difference. So people can visually understand that the number of dots above are roughly the same as the number of dots below. But when I change the axis to this scale, it appears that there are more dots above than below. What about these two? Are there any difference? Come on, guys. Young guns. Yes.
Here this is like the same.
Where's the maximum data in this?
In the left.
0, 1. Somewhere around 1.
Yes.
So they just move the 1 to the center here, and other data on this side and other data on this side. Because they changed the x-axis to logarithmic scale. Here the y-axis was changed to logarithmic scale. So you must think clearly, if I'm trying to show the picture like this, I can change. So the difference in the bottom panel is the histogram, the y-axis is linear here, logarithmic here. So you can often think that if I want to produce a graph, is it better to keep linear scale or logarithmic scale? Okay. Now, the linear scale, previously before apps were called widgets. Okay. So the number of apps, let us say apps for smartphone, has suddenly increased from the year 2005. It appears like that because the x-axis is on a, y-axis is on a linear scale. But if I change the y-axis to logarithmic scale, it suddenly looks at the change, or the rate of change has remained the same. So this linear scale is also called panic chart. Crime, domestic violence, IV drug abuse, it'll all look like this. But if you put it on a logarithmic scale, suddenly it doesn't look so bad. So you can decide, you should not try to manufacture a story, but you can make any story you want, and that's why this linear scale is often called panic chart. I did this graph myself, okay, and you can all go and do this as homework. But today you must go to PubMed and put withdrawn papers. Withdrawn papers mean people publish and then somebody said, hey, this is fraud, fiction, some problem, take out the paper. And this is the graph, and you can download that data from PubMed, it's free, into an Excel spreadsheet. And this x-axis is 1970 to 2025. And 2025 looks a bit small because only Jan data. That's why it suddenly looks less. Okay. Otherwise, it's not that all of a sudden things change. But does it look like, what does it look like? What is panic or no panic? And panic. It appears that the world is full of fraud. Now, people will sell a story. During COVID, people started sitting at home and manufacturing data and writing papers. That's what you can sell a story. The effect of COVID on, people's integrity. So what did I do? I Googled and found out in an Excel spreadsheet how to change the y-axis from linear scale to, and you can all find out. It's a simple thing. You just go there and change the axis, y-axis, change to logarithmic scale. And this is what I got. From 1980, it's gradually going up. It's not suddenly all of a sudden during COVID, there was a huge change in the amount of withdrawn papers. So it all depends on what story you want to tell. You must not tell a false story. So if it's possible to show the graph in logarithmic scale, use a logarithmic scale. I can't use log scale for the x-axis because it is time. I cannot change that. But the y-axis here I can change to you can mathematically do anything, but you must think what makes sense to you. Okay, symbols. Symbols should be intuitive, and these are not difficult. Plus means positive, negative means minus means negative, and 0 means neutral outcome. So the legend must also be clearly given. Just because you put plus and minus, somebody else may not understand what is plus, somebody else may not understand what is minus. All right, this is looking at, it's a recent paper published in 2024, I think, in Lancet on undiagnosed diabetes from 1990 to 2022. 140 million people. So it's not a small study. They collect global burden of data from every country in the world. So it's a large study. What do you think the size of the circle tells you? Proportion of undiagnosed diabetes. So where is India? Here we go. India. What is 133 million, you think? Number of people with undiagnosed diabetes in India in 2022. What is 30% mean? 30% Indians? Globally, among all the undiagnosed, 1 in 3 are Indians. So, somewhere we have to shine. So, we are shining like that. So, the number of people with untreated diabetes who are more than 30 years of age, correctly you said, the circle size is proportional to the number of people with untreated diabetes. And these are the top 20 countries in 2022. Though there's much more data, but this picture is for 2022. And there's rankings. So they put the ranking 1, 2, 3, like that. So number 2 country is China, like that. So you can have a look. So obviously there's something we are doing which is not so great, which is leading us to this problem. And the number in bracket is this percentage is compared to the total global burden, not to the population of India. So you can choose these circles and pictures and symbols very carefully. Now sometimes you have graphs which have got triangle, circle, square. There's no ordinary immediate understanding of what is circle, triangle, square. So you'll be careful when you use circle, triangle, square, and then unless you explain clearly to the reader what is circle, what is triangle, what is square. Okay. So let's have a look at this. This is a paper which was published in I think 2024. It's looking at the safety of COVID vaccine, adenovirus COVID vaccine. Okay. That's the topic. On the x-axis is 0 day after giving vaccine, 14 and 28 days. And the colors you see, circle is low dose, square is middle dose, red is high dose. If I don't give it the legend, you won't understand what is green circle and what is red triangle. So you have to give a legend along with that. And this is the interferon gamma expressing cells per 10 to the power peripheral blood mononuclear cells. So whatever it is, you can see that from day 14, day 28, between low, middle and high dose, how the comparisons are. These triangles and circles are useful because in this particular picture, they thought this is a nice way of showing the picture. The colors add to that. So you must decide what you want to do and how to show it. So don't simply put colors, circle and square, but you must explain what they are. Legends. Legend is, what is this? This is a legend. Low, middle, high, the legend for the circle, square and rectangle. Legend should not take up too much space. Sometimes you have a big legend in the picture that's covering up the data. So they should be placed on the margins. So you can see that this legend is kept here, margins of the figure. And the legend for the x-axis, y-axis is below the picture. If there's only a single line, you can keep the legend on the line or close to the line. Very important. This is 1991 to 1999. This is the stock market, how it's doing. Now, what is India's stock market called? What is the index called? What is the index called? So in the US, they have FTSE, DAX, other countries. So which of these is doing well? We didn't see the legend. We didn't see like that. So you have to now think, oh, what is purple? Then look at purple. You see the same thing here. Next to the picture, they put the purple, DAX, FTSE and SAC. So you can choose. No, I want to keep the legend outside because you told in one lecture, keep legend outside. No. In this particular picture, the legend inside appears to make reading of the graph much easier. So where you keep the legend is very important. You can change it slightly according to your convenience to make readability. Remember, the audience is who the hero of the story is. They must understand what you're trying to say. So, okay, I've shown you this. Orientation. If there is an order in the data, bar plots. I don't know if you remember last time I showed you bar diagram, histogram, and things like that. Bar plots. So showing the data as horizontal bars and sorting out from lowest to highest is more easy. when you have a bar chart, showing them in horizontal is easiest than showing the bars as vertical bars from left to right, except if time is an issue. Now it's a bit complicated what I'm trying to say, but the picture will tell you this. Okay, remember I said, okay, this on the yellow graph, we are comparing the change in the GDP in 2017. So which country had the highest change in GDP? China. More than India? Because you can compare horizontally and we have put highest to lowest. So visually it becomes very easy, right? So that's what I said, horizontal bars are easy. When you order them, then you don't have to change color also. This is an easy way of horizontally ordering. And I told you that except when time. So if time is there, 20, this is only Brazil. And this is the growth in GDP in Brazil, 2010 to 2018. Because time is there, I can't stack up this on the y-axis. Time has to go this way because we're all used to seeing time going on this x-axis like that. Then we can see, oh, in few years the GDP was going up, then suddenly the GDP fell minus, then it went up again. And then even added who was the president at that particular point of time to make a political story. So and so Dilma Rousseff did well, and Lula did badly or good or whatever. So you can make a story like that. So these bar charts are very useful like this, except if time is involved in one of the axes. Okay. Box plots. I'll show you a box plot. For box plot, horizontal orientation shows more accurate than vertical. And I'll tell you why. Right. So I'm going to ask the statistician what the box plot is in a few seconds. So horizontal is better than. Why is horizontal box plot better? In the middle of the horizontal box plot will give you the median value. And if you want to compare median values, vertical lines are easy for the eye to compare than horizontal lines. Now this is a theory. Let's understand the picture. Which is the horizontal box plot? This one or left or right?
Right.
Picture on the right. So these are the vertical lines, which is the median. Okay, let's ask. What is a box plot? What is this? Is this the 25th percentile value and this the 75th, or this is 25 and that is 75? In a box plot. Come on, stats guys. Yes. Aris. 25. So this is 25, 75 median. Okay, anyway, some homework for everybody. Box plot. We're trying to compare these black lines. We can compare them easily this way, and this is A1, A2, A3, B1, B2, B3. Clearly, there's some difference. Now, you may argue, no, I can compare this way also, but the general scientific idea is easier to compare this way, the vertical lines, than to compare this way. It's your choice. You can choose which way you want to produce box charts, but this is what people have said. Okay, this is the miles per gallon, different cars, and this is the highway. What's the problem with this access grid? There are many cars. Yeah. Yeah, you are pointing to something. Girls, what is the problem with x-axis? Can you read x-axis? We can't read x-axis. So I just changed the graph. X-axis became y-axis. So now each car, highway mileage, and I can compare the mileage this way. Here I can show every single car's name. When I put the same thing here, what happened? Suddenly it became crowded. So the axis and legends, you can sometimes decide that, okay, it is important for me to show every single car, and I want to compare the highway mileage. Therefore, when I put this in the y-axis, the axis becomes clearer and comparison becomes easier because I'm comparing the vertical lines in the middle. Yeah, you got it? Now you must have some thought. How am I going to show the axis? Okay, this is called chart junk. Can you see the number in the x-axis? You can't see? Let's see. 1, 2, 3, 4, 5. What's the problem? All these colors which people love, is masking the real data. Somebody can't hear? Here, okay, okay. So this is called chart junk. Often all of us do this. Let's put colors for this, color for that. You can just click and put fill color, patterns, zebra, all this 3D effect. This is a problem with chart junk. So we must totally avoid this. As far as possible, simplest picture is the best picture. These are 4 imaginary countries and there are shaded colors. One may imagine that whatever disease you're talking is more here and less here. But that was not the story of this particular paper. They simply put colors and put some, what is that called? Shading. It doesn't look nice, but it is not good for a medical picture because it implies that there is some gradation in disease or population or something. So never use this gradation or shading in medical pictures unless you're trying to tell a picture. So this is the second chart chart. This I made from deep AI as an AI generator. What do you think is the story in this picture? Concert, okay, maybe the concert, and that's the musician. What was it? Actually, the star is the star of this. What's the problem? Some people are very good at photography. When they take photo, the person will be the main thing. When I take photo, most of it will be background and the person will be somewhere in the photo. So my kids will be like, don't take photo. You don't know. We won't be there in the photo. So what's the problem? Too much of other elements in your data. What should I have focused on? The star. Instead of that, everybody got distracted by somebody said concert, somebody said northern lights, somebody said statue. So the elements of the data visualization should not distract you from the main story. So be wary of chart. The data should be the star. What is the data? The main message of your picture. That should be the star of your picture. Okay. Let's look at this. Can you see this now? How many panels there are in this graph? 1, 2, 3, 4, 5. But there are 6. What is the advantage of this particular panel? The y-axis highway miles per gallon, 20, 30, 40, 20, 30, 40. There are actually 6 different subgroups here. And there's the engine displacement, 2 liters to 7 liters. And types of engine could be 4, F and R. This is 1999, 2008. Now they're trying to show lots of data in a single graph. So you have to decide whether this highway miles per gallon now has become a common y-axis. Engine displacement has become a common x-axis. I can show a lot of information in a single graph. Some people look at this and say chart junk. Too much information, I can't make out the story. Somebody else will say, no, this is very clear and the colors mean something. Now I have to interpret what is that red, what is blue, what is purple. So you have to have an idea that sometimes it could be too much information for the story you want to tell. Sometimes it may be too little or just the correct amount of information. So now the next one. This is the change in diastolic blood pressure and the systolic blood pressure. So the stats people, we did scatter plot recently, systolic blood pressure versus diastolic blood pressure. Okay, where does the x-axis start? So always x-axis this way is 0 and y-axis upwards is 0. So always there must be a line in the graph for x-axis, y-axis at 0. Is there a good relationship between diastolic and systolic blood pressure in this picture? As the diastolic goes up, does systolic blood pressure go up? Yeah. What could have helped? A diagonal line. If they put a diagonal line like that, that will show you that as the systolic goes up, diastolic also goes up. The perfect diagonal line is there's a 1:1 relationship. 1 unit change in diastolic, 1 unit change in systolic. So they could have added that line. What does this extra line 80 mean? Why did they put a line at 80 in diastolic? Why do they put a horizontal line at 130? Normal. So then you can say, oh, all the people in this left lower quadrant are people with normal blood pressure. What if another country had 140 by 90 as a cutoff? 140 by 90. So you can see the extra people here. What are these people called? What type of hypertension? Their diastolic is less than 90, but the systolic is like isolated systolic hypertension. Similarly, these people here, they don't say isolated diastolic hypertension, but they're people with high diastolic but normal systolic. And these are so these kind of grid lines, few lines like this here, not too many. That helps you to understand much more than just keep. If I just take out all these lines and simply put one scatter plot, and say interpret it, then you may be like, oh, okay, that's a bit different. But these additional elements are helpful, right? So you have to choose additional lines carefully. Okay. Can you see this? This is a change from baseline. This is time. Okay. And this is placebo. This is the active drug. Which of these say all three graphs are same? Which graphs you like? That's fine. All are same. Why does the line help you? Correct. It gives you a visual thing. Where is the zero? Where is the child? No change. Right. What is the difference between this picture and this picture? You see that the amount of space above here is less and here seems more. Here they have just put the zero so that the minus 100 and plus 100 come. So the picture looks correct. So you all got the principle now, how to make a picture. So you can see in this figure, from a starting point, time zero over time. So this figure requires you to visually make a zero line there. Correct. But here we put one line. The line makes it easy to interpret above and below the change. And you can see that this is much more below and this is much less above. So the third line here, what I've done, I've just made the picture look symmetric. So this is less here. I mean, this is same here as here. So this is how one must actually produce a picture. When you're comparing placebo versus active, you must put a zero line, show the curves, and you can make the graph symmetric above. It's all just a matter of changing the options on the software to create a graph like this. All right. Okay, we're almost coming to the end. I know it's a longish class today. Now, scatter plot may sometimes look like this, right? And you may wonder how to make sense of the data. So has anybody heard of this? LOWS, locally weighted scatter plot smoothing. So instead of putting a graph which goes through every single point, it looks really haphazard. Then we try to make a smooth line across the data. This is called LOWS, or some people call LOS, locally weighted smoothing. Right? So different words people use for the same thing. So sometimes in scatter plots, you can also click the option lowest plot or lowest plot. I don't know if pronunciation is right. And then you can get a line which looks like that. Now, sometimes not only they show you a line, they show you a light pink line around this dark red line. That light pink line is the confidence interval. So for each point, how much it could have varied, 95% of time. If it makes sense to the reader, show that 95% confidence interval. If it doesn't make sense to the reader, we need not show that 95% confidence interval. Now this is a graph comparing for abdominal surgeries, transversus abdominal spleen infusion with bupivacaine. That's one. Epidural anesthesia is one. Giving intravenous opioid. So three choices for abdominal surgery. This is the time zero at surgery, and this is time after surgery, and this is pain. This is called lowest plot. Why lowest plot? This is the dotted line. The green one is opioid, and this is the confidence interval around that. The transversus abdominal spleen infusion is the blue one, and the red one is epidural. So instead of just showing numerous scattered dots there, they have done this smoothing to make sure that you can see a pattern. Otherwise, it looks like hundreds of colored dots and you can't make out a pattern. So you can use the smoothing technique to get beautiful pictures. Lastly, we are going to three-dimensional charts. So 3D charts, sometimes people like, it looks very nice to have a 3D chart because people will be like, oh man, this guy's made a clever graph, right? But it's very difficult for people to interpret. You see this, what is the value of this point? How did you read that? So from 10, you have to go there, go all the way and say, oh, that is 10. So it's not very easy to interpret 3D graphs. So as far as possible, avoid doing 3D graphs. Okay, what about the graph on the right? Good graph, not so good graph. There are three axes, 1, 2, 3, A, B, C, D, and then 10, 15, 20. Lot of information. Does it look like there's some sort of a trend going on? Increase or decrease in data? What, Rachna? Some sort of changes are there, right? Okay. Actually, the data is just going the same 10, 20, 30, 40. In every row and column, the data is the same 10, 20, 30, 40 in all three axes. But it appears from this picture that there are some trends beyond just this steady increase in every axis, right? So, reading from 3D charts is very difficult. So, many complicated journals, basic science will produce 3D charts and then nobody can understand that 3D chart. Okay. This is a very nice website. I want you to try looking at this website. Data visualization, this guy Praveen Purohit. Like that, what happened to that cheese? Is the cheese in front or back? It's given a 3D impression that this cheese piece is in front and this cheese is slightly back compared to that. Bracket is the same cheese piece with this same thing. The brain perceives that the one which is occluded is behind. It looks like that whatever rectangle is behind. Which is not true. It's the same plane. So 2D objects try to make it 3D, you start perceiving it differently. Okay, this is apples, banana, orange. Look at this picture first. The number of apples is 5 and number of banana 5. Apple is blue and this gray color is banana. Are they same size in the Venn diagram? Blocking. What do you feel, Reba? These two are same. What about this picture, Reba? It suddenly appears that this blue apples seem to be less, where banana seems to be more. Why? The same effect. It appears what is farther away is less, closer by is more. So if you produce the same figure in 3D in Excel spreadsheet, it will look very nice. Ah, clever picture. But you're misleading the reader. That suddenly that one fruit is more than the other fruit, when actually both are same. Another picture which he has shown. Okay, I'll explain this. Now, this is comparing potato, tomato, cabbage, India, US, UK, France. Let's look at this. India 5 for potato, okra 5. Okay, so let's look at potato. Green is India 5 and okra 5. Okay, then we can compare between India and UK 5, 5 for potato. So you can see UK same. But now let's look at this graph. Suddenly, where can you find this data? This is the same graph as this. I tried to show the information as 3D. Suddenly, you're not sure whether this is a trend here, there's a trend here, or there's a trend going up like that. As far as possible, avoid showing 3D charts because the data here looks less, data there may look more, or vice versa. This may look more and that may look less. So avoid 3D charts as far as possible. This is simple, but just looks fancy. Tables. The general rule is if you have small number of data points and precise numbers, 1.112, those kind of things, when decimal points to the x degree, put it as tables rather than figures. For readability, tables are as good as figures. Some people say, no, figures are better. No, tables can be as good as graphs. Okay. Now let me ask you, I want to compare product A, B, and C in Africa. Nitish, which is more? In Africa, which is more, A, B, or C? Okay, the same graph. Which is easier to read? Comparing in Africa. What Rachna, which is easier to read? This way or this way? Right? What is product? Product maybe hashish. I'm joking. Maybe apples, oranges, whatever. But generally, human eye is able to compare this way. So we must put column-wise product rather than put the column. You can do anything. Like change x-axis, y-axis in Excel or SPSS you can do. But generally try to prefer this. If this is the story you're trying to tell, comparing product A, B, and C in Africa, which is the maximum. Right, here is as if you're comparing Africa, Asia, Europe, and North America, then you can put the graph this way. What you're trying to compare must be in this column-wise. Okay, so last time I told you all, there are many styles, no? What style of table is this? American style. NHM style. A psychiatrist, where is a psychiatrist? Finished and left. American Psychological Association, APA style. They are the style which most people in the world follow. How many horizontal lines are there? I'm blocking you. 1, 2, and 1, 3 in the bottom, which you can't see. How many vertical lines are there? 1 this side, 2 on this side. Normally, when you put Excel spreadsheet, it's full of like a grid, right? How do we read? Left to right, vertically. What is the easiest way for the brain to read? Left to right. That's why they don't have any more vertical lines in all the top journals have no vertical line. Correct the demography, age, here. Right. And to differentiate the vertical lines, you can use light color or just give some space. So this is the actual way a table should be done. Table title is on top, figure title will come in the bottom. These are some general conventions of table and figure. How many decimal points are there in this whole table? Different data. We must try to be consistent. For some data, don't put 1 decimal point. For some other data, don't use 10 decimal point. SPSS will give you 5 decimal points for everything. You must read the instructions to author for every journal. That instruction to author will tell you how many decimal points they want for their tables and figures, and you must follow that. Generally, don't put more than is required. Showing 3 decimal point doesn't make you cleverer than somebody who put 1 decimal point, right? For example, let's look at systolic blood pressure. Have you checked blood pressure? Have you ever checked blood pressure to decimal point? That itself is a bit of a stretch, right? Unless you have some very sensitive blood pressure machine, we don't check in decimal point. If I put 2 decimal points, what sense does it make? No. So a little bit of thought must go into your number of decimal points. So unnecessary precision should be avoided. Okay. Now, this is looking at slightly different thing. This is looking at artificial intelligence and doing Gram-Stein microbiology. Yeah.
She used the row percentage of the column percentage.
Ah, good idea. Last time the stats guys, I took class for you all. What are we comparing? Empagliflozin versus placebo. So if I want to compare what 63 versus 63, I'm comparing these two. So column percentage. So that's why you must know I'm comparing empagliflozin versus placebo. Column percentage. That will be given by a continuous data t-test. If it's not continuous data like something yes or no, diabetes yes or no, chi-square test. So always generally you try to compare the two things in columns and use column percentage. generally. Let's look at this. I want to look at how good artificial intelligence is in reading some gram stain. Don't have to worry what it is. And the last two columns, sensitivity and specificity. In AI, sensitivity is also called recall. Then they have specificity. Here it made sense for them because the values are very close. How many decimal points are there? 3 decimal points. Because everything begins with 0. And that sensitivity, I can express it as 94.5 or 0.945. So they have chosen to use it as 3 decimal points. Just to show you that you must be really careful. That journal didn't want sensitivity 94.5. They wanted it as a decimal point. So you are forced to put 0.945. Here you can't put 0.9 because 0.9 compared to 0.9 looks same. But 0.945 is different from 0.910. This is 94.5, that is 91.0. So to be very careful about the number of decimal points, but you can't say that for these two I'll put 3 decimal points, here onwards I'll put only 1 decimal point. Keep it uniform in your tables and figures. Okay, alignment of numbers should be so that it's easy to read. In Excel spreadsheet, this is how Excel default does. Text is where? Left or right? Left. Numbers are to the right aligned. So who has is sales more or expenditure more without reading the numbers? Sales is more because it's extending more this way. So visually, if you start numbers aligned to this side, then the more you go this side, it seems to be more. Whereas text is always aligned this way. So there's a simple tricks when you're doing Excel spreadsheet alignment or even tables and figures. Alignments can be done in this way. So if you have multiple tables and figures, is this a good way of showing mean and standard deviation? Some people will say, no, this is not a good way of showing. Shall I show it like this? So you have to decide. Any JM may prefer this looks nice. Then somebody else will say, okay, maybe the standard deviation instead of being times New Roman 12, we can put that as times New Roman 10 to show that that is the standard deviation. Somebody else says, no, this looks very nice. Everything is very clear. So you have to decide as a reader, what does your reader like? Is the standard deviation a very important variable? Maybe in a stats journal, SD has to be shown separately. But general medical journal, they don't mind this. But a SAS journal may want this kind of. Somebody else will say, no, keep it like that, but change the font in this. Somebody else will want this kind of way of showing the data. So when you have multiple data confidence intervals, look at that journal. If I was not submitting any jam, I'll submit like this or like this. The top column or bottom. Because I know that any jam wants this style. As the previous any jam picture. This is the New England Journal style. They don't even put mean or standard deviation. They just put the number and bracket. So I will just use that when I'm submitting to any jam. I'll just use this 69.8 plus or minus 17. So look at that journal which you're submitting to and then decide what is the guideline for that particular table. Orientation. This is called portrait, counseling. This is called landscape, and this is square. Okay. So very often you'll have a mega table, and the table will be going on into 3-4 pages. You call it COP village. Suppose it baseline characteristics, it will be going on into numerous pages. So how to do? If you put portrait and go, you can change it to landscape. So this is the example of a landscape from New England Journal of Medicine. This was looking at the title of extrapancreatic neuroendocrine tumor compared with pancreatic neuroendocrine tumor, and I'm looking at cabozantinib versus placebo. Is it easy to read? No, but the whole table is in one page because I chose it in landscape mode. So how should I read? I have to do like that. Or in PDF, I must go and put change to clockwise or counterclockwise till I get the orientation. This is another one. Global burden of gout. This is in Lancet. They like portrait mode. So the single table is going on into many pages. So then you'll be going on reading this way. So you have to decide which one, landscape or portrait mode, is better. So general guideline is landscape is discouraged. This one is generally discouraged, but NEJM seems to like large tables as landscape mode. Lancet seems to like portrait mode. Fonts and colors. This is my last slide. Do you think the use of colors is good or bad? This is the computer language. This is the intended use. Whether that language was imperative or not, whether the object was oriented, and whether standardized, yes or no. Did the color help or the color didn't help us? They are arguing the color helped because all yes became blue, all no became orange, and everything else remained in green. Okay, you can make a choice, right? So don't put too many colors unless it helps you tell a story. Okay, let's recap. All this material, the baseline material came from Royal Statistical Society, Principles of Data Visualization. I've just taken pictures from the net. I've tried to give acknowledgement wherever I've taken from. Any questions? These are just to help you when you make your own data visualization. This is part 2 of the talk. Any online questions? No questions? Maybe it was confusing or everybody's has gone a little more than time we planned. If there are no questions, then we'll thank you all for coming. Okay, see you next Saturday, guys. Bye.